Hello and welcome to Atheists Talk. My name is James Zimmerman. I'm going to be your host for this show. We're actually going to do two-part shows on climate change, questions that people have about it, what exactly is meant by the definition, and some of the controversies. So my guest today is Greg Laden. Welcome, Greg.
Thanks. Nice to be here.
Let me give you some background about Greg before we go any further. I'll just read what you wrote me here.
Okay.
Greg is a science communicator and teacher who has studied the relationship between human evolution and ecology, climate change during the Holocene, and African and North American prehistory. He's addressed mostly through his writings on National Geographic science blogs, The Science of Climate Change, and you've presented several talks and workshops on the issue. Your writings appear in the book Atheist Voices of Minnesota, which was published last year. You're also currently writing two books. One of them is on field work in the Congo, and the other is a novel on life in the upper Midwest and Plains in a post-climate change world. And you strongly hope that that novel remains fiction and not prediction. You live with your wife and your two kids in Coon Rapids, Minnesota.
Yep.
So again, welcome.
Thank you.
So the first thing that we want to discuss about climate change, since this show is called Atheists Talk, is why should atheists care, or why should it concern atheists in particular?
Well, first, I think it concerns everybody, and so obviously any group of people interested in important current topics. I think it's especially of interest to atheists because there's a big overlap in the atheist community and the community of people who are interested in science communication, skepticism, that sort of thing. So, and it happens that climate change isn't just another science. It's a science that has been, along with the climate change science and activism, has developed an anti-climate change activism and science movement. So we're seeing, just like with evolution, atheists are interested in evolution and teaching evolution because there is a very strong religiously driven anti-evolution movement. And the skeptical movement opposing climate change has a lot of overlaps. In who's involved in it, what their motivations are, and so on. Just today, I don't always remember his name, but a famous conservative religious talk show host from, I think, Fox News or something, tweeted. Yeah. He put out a tweet saying the difference between climate change and Jesus is that Jesus is coming again. Okay. And I'm not sure why. That doesn't really make sense. I guess climate change is not. I don't know. Whatever. So there's actually an activist side of it. There's an atheist versus people who are not only religious but imposing their religion on other people. One of the reasons to oppose climate change science is religious.
Okay.
It's been members of Congress have stated that it's actually sacrilegious to think about climate change science as a thing, because this is God's earth and God will take care of everything and so on. So it's really there's a lot. It's not as clear as the evolution creationism difference, but there are a lot of links and a lot lot between them. Yeah.
I guess when I think about other issues that have gone into the political sphere, maybe such as abortion, a lot of it is not just political, but also because of people's religious beliefs. Yeah. Definitely true. We see that with evolution and with abortion. You're saying so that it also comes into play with climate change.
Yeah, it's not as thorough, it's not as across the board, but there's definitely that element.
Yeah.
For sure.
Okay. Yeah. So actually, before we move any further, we should talk about what exactly climate change is, right? So that we clear up any misconceptions. So what exactly are the basic physics of climate
Well, okay,
change?
First, the term climate, people actually, everything's controversial. And people have a controversy over the use of the word climate change. People will argue that it was invented or adopted by various groups to address certain political reasons, and that to replace the term global warming. What we're really talking about here is anthropogenic climate change because of the release of previously fossilized carbon in coal, oil, gas, that sort of thing, into the atmosphere. And the main effect of releasing that carbon into the atmosphere, mostly in the form of carbon dioxide, is global warming. So when we talk about climate change, we're mostly talking about global warming. Mm-hmm. We could just use the word global warming and that would work, except there are a few things that aren't global warming that are related to this, such as acidification of the oceans, which we're probably not even going to really get to. But it is global warming. Basically what happens is, the sun shines on the earth, so energy from the sun lands on the earth. It more or less, in a very simple version of this, it more or less passes through the atmosphere, hits the surface of the earth, and heats it up. So the surface, the ocean surface, the land surface, gets hot from the ocean, from the sun shining on it. As you know from just walking on pavement in the summertime when it's warm out. And that heat is now the same energy that the sun put there, but now it's in a different form. It's now infrared radiation. And that infrared radiation basically leaves the Earth and goes through the atmosphere back into outer space again. And if our atmosphere either didn't exist or consisted only of certain elements, then it would be a very different system than we have now. If our atmosphere was only nitrogen and oxygen, that heat would more or less quickly go back into outer space again. It wouldn't take long, and we'd have a very cool atmosphere. But there are some gases, notably CO2, in the atmosphere that cause the heat to not get back into outer space as fast. And that's an interesting phenomenon. It's a sort of a quantum physics level phenomenon. You know those old toys that came out a long time ago, but they're still kind of popular? You give it to somebody who already has everything else. It's a bunch of ball bearings. Each is suspended on two strings.
Oh, sure, yeah.
You lift one up and let go of it, and it hits the other line of them, and the one on the other end pops out.
Yeah. Newton's cradle?
Newton's cradle, is that what it's called? Okay.
I think so.
Well, if the air was made of just nitrogen, for example, it would kind of be like that. That's heat coming into the bottom of the air, just more or less goes without any incident to the other end of this atmosphere and leaves. Okay. A greenhouse gas is a molecule made differently than one of these ball bearings. It's more or less, imagine 2 or 3 ball bearings held together with springs, so they're all wiggly wobbly in the middle of one of those Newton's cradles. If you release the ball at one end, the energy would go into the middle, and then it would just be the springing around. The energy would just kind of be randomized. That's what greenhouse gases do. They take this infrared energy, and they absorb it, and then they send it out in a random direction, and instead of towards outer space, where it was heading originally. So that slows down the departure of this heat from the atmosphere. I also like to think of it as, imagine that the surface of the Earth, the heat on the surface of the Earth is a letter you're putting in the mailbox. And the heat leaving the atmosphere is a letter getting to its destination. And in between all the molecules are the postal workers. So the guy comes to the post box and gets the letters, drives them to a place where they're put into bins based upon the first digit of the zip code, and then they're further sorted, till finally they're organized, and a postal delivery person takes them in a truck and takes every letter and drives them right to where they're going to go, puts them in the box. Now, that's fine. Imagine that 1 in 100 postal workers are totally stoned, and their behavior is utterly random. So they're not sorting anything, they're just randomizing things. Only a few, though. Only 1 in 100 postal workers are doing that. That would actually slow down the average rate of delivery significantly. Okay? So a very small number of molecules in the atmosphere acting like drunk postal workers causes the heat to stay in the atmosphere longer, which is a good thing, because otherwise it wouldn't be very warm on the Earth, and we kind of need that warmth. Problem is, over prehistoric time, we know that the amount of carbon dioxide in the atmosphere has changed a lot. It has been historically, in recent thousands of years, under 300 parts per million. In the past, it's been over 1,000 parts per million or 400 parts per million, different values in between. And whenever it's at a higher level, the energy in the atmosphere is retained longer, and the Earth is significantly warmer. And we are currently moving the amount of CO2 in the atmosphere to levels that haven't been seen in millions of years. So we're transforming the atmosphere over to an atmosphere that existed long before humans evolved, long before anything around any of the ecological systems we have now existed. And it's not impossible for life to exist on a planet that's much warmer, but it's a very different planet.
Yeah.
There's another catch. I don't want to frighten people. People who talk about global warming as though it was real, which it is, get called alarmists sometimes when they mention this kind of thing. But the physics here is the release of carbon, mainly carbon dioxide, into the atmosphere, changing the nature of the atmosphere. That carbon was originally fossilized from the atmosphere. And it's probably true that large amounts of the coal and oil that we have now formed, especially the oil, formed during periods of relatively large extinction rates and very low productivity, bioproductivity. One way in which oil formed, a lot of the oil reserves we have now, formed in an ocean that was anoxic. So only organisms that use oxygen only existed in the top few meters, maybe the top 100 meters, maybe the top 10 meters. And everything that lived there that died, that went into a lower depth, rather than becoming eaten by something down deeper, became potentially petroleum. And that's how we got those petroleum reserves. So every now and then the oceans and the Earth do something really bad, mass extinction happens, life gets kind of tough probably, and we get oil fields forming for 10 million years at a time, every now and then or so. And that's how that oil got there to begin with.
Okay,
and coal is
yeah.
a somewhat different process, but it's a similar but longer term, slower process.
So when you mentioned the molecules, it
Yeah.
sounded like CO2 was the major offender. Are there other gases
Yeah,
too?
CO2 is a major offender because it's one of the most common greenhouse gases is water vapor. We are not doing something that puts water vapor into the air, but because we have warmed the air by adding CO2, there's more water vapor in the air.
Okay,
We've
yeah,
increased the
because
water
it'll
vapor by
hold
about
more,
5%. We can come back to water vapor later because I think it's going to come up again. Methane is probably 20 times more potent of a greenhouse gas than carbon dioxide is. But methane breaks down into carbon dioxide and water. It doesn't take that long. So if you put a bunch of methane in the air, you can actually get immediate and dramatic warming locally, even as the methane just sitting there before it's dispersed. And methane is a significant contributor. But over the long term, if we stopped letting methane into the air, and some of it goes in naturally, and we're putting some in, all the methane would be gone in just a matter of years.
Okay, yeah.
The CO2 does not go away. Interestingly, individual CO2 molecules do leave the air. An individual CO2 molecule might be in the air for only a very short amount of time, but it switches place with one that was in the ocean. The ocean and the air are constantly exchanging CO2.
Yeah.
The ocean is part of this system, a very much important part. So the CO2 that we're releasing from oil and coal is more or less in the air indefinitely.
Okay. And then when we talk about the atmosphere and these gases piling up in the atmosphere, are you talking the bottom 100 feet where humans are doing most of their activity, or are you talking up several miles?
It's the whole atmosphere.
Okay.
Exactly how it works and what happens. And this is sort of a little bit beyond what we can probably talk about here, but the troposphere is the lower part of the atmosphere where most of our weather happens. A lot of our weather happens above the troposphere, at the interface of the troposphere and what's above it. But what happens in terms of warming and cooling it depends upon whether you're looking at upper and lower. We may be actually experiencing upper atmosphere cooling as we're experiencing lower atmosphere warming, and that's because the energy that was passing into outer space was warming everything a certain way, and now we're holding it down lower more. There's more air molecules down lower. So we're actually warming the lower atmosphere more than the upper atmosphere.
Okay, yeah.
And that results in cooling the upper atmosphere a little bit. But yeah, the CO2 is distributed more or less uniformly.
So one of the main disputes that people have is they'll say this is just a natural variation, one of the Earth's cycles. You even mentioned that there's a cyclical nature to the amount of CO2. Or is it possibly just the sun acting up? We know that that has a major factor on how the Earth operates.
Yeah. The sun brings in there's two different things that the sun brings in. One is the sun itself is stronger and weaker over time. It changes in how much energy it gives us over time. So if the sun got hotter, it could make the Earth warmer, cooler, make the Earth cooler. And that is, if you look at actual surface temperature measurements, by surface temperature we mean the weather stations on the ground all around the world, plus the sea surface temperature, added together and averaged out. When we look at that surface temperature of the planet, it's a squiggly line. It's been going up, but it's still a squiggly line. And part of that squiggly line has to do with basic natural climate changes within the system, like the southern oscillation, El Nino, that kind of thing. And part of it has to do with the sun getting stronger and weaker over time. But lately, so the shapes of the squiggles are partly determined by the sun, but the sun has actually been getting weaker. We're in a period now where the sun is producing less energy as the global temperature has been going up. So it helps shape the squiggliness of the line, but it isn't causing the line to go up. It's actually helping to let the line not go up as much as it otherwise might.
Sounds like it's counteracting
It's counteracting it a little bit, but it isn't very strong of an effect. It's not a very strong effect. The other way in which the sun, and sometimes you see people who want to deny climate science talk about this, there's a large-scale phenomenon called the Milankovitch system, in which Milankovitch cycles. Okay, the Earth's orbit is an ellipse. The ellipse gets more elliptical and less elliptical over time. Where the Earth is on that ellipse on a given day changes, because the Earth doesn't just go around the ellipse as it actually moves in relation to so the June 22nd can be when the Earth is as far away from the sun as it can be, or when it's as close to the sun as it can be, and it moves in between. over many thousands of years.
Yeah.
And then the Earth also tilts. The Earth is tilted
Yeah.
slightly, but the amount of tilt changes. Those three numbers result in this complex orbital geometry that does determine the overall strength of the sun at a given point in time. And what we know is when we're having year after year after year of the northern hemisphere, because that's where most of the land on the planet is, when the northern hemisphere in the temperate regions, say at 70 degrees north or less, is relatively weak sun during the summer solstice, the Earth tends to have ice ages. And when it's the opposite, the Earth tends to have interglacials. That is not the reason why we have ice ages and interglacials. Ice ages and interglacials come and go for a wide range of reasons. This is a more or less necessary but not sufficient condition for an ice age. So people look at that and they say, well, we're coming up to a period soon, meaning next century or two, when we should be having an ice age. So maybe global warming will just stop us from having an ice age. Or this has a larger effect than CO2. The problem is this whole ice age thing that I just mentioned has only been going strong for the last 750,000 years to 1 million years, and weakly for about 2 million years because of other things going on, mainly the lack of carbon dioxide in the atmosphere. So when we add carbon dioxide back into the atmosphere, the Milankovitch cycles, which are a solar thing ultimately, stop having much of an effect. They stop causing ice ages to come and go. So we now have enough carbon dioxide in the atmosphere that I think we can kiss the Milankovitch cycles goodbye. I don't think they're a factor anymore.
Yeah. They've been overridden.
They've been overridden, basically, yeah.
Some people talk about a pause or a hiatus. Is that the same thing in global warming? Is there such thing as a pause or hiatus right now? Or?
Yeah, the pause is there's two ways you can get a pause. One is there's this squiggly nature. The standard line, you can get a lot of different data sets and make any one of several different squiggly lines. And in climate science, in paleoclimate science, we call those squiggles. There's a squiggly line of the temperature over the last several decades or last century as it goes up. There's one way to show that temperatures are not warming is to pick a certain point in time when they were cooling. I think it's interesting that in the 1940s, during World War II, early 40s, is when the number of weather stations went up way fast because everyone in the war needed to know the weather all the time.
Right.
So suddenly there's weather stations everywhere.
Yeah.
Okay. So if you looked at the 1960s, you have 20 years of actually kind of a lot of data. But between the 1940s and the 1960s, the Earth was cooling. The squiggles were going down. And then they started to go up. And then in the 70s, Pinatubo went off and it went down again. So if you take any given decade or so, you can have a downward trend or an upward trend. And so you can pick a downward trend and say, see, it's cooling. But when you look at the larger picture, it's definitely warming since the 19th century. In the last couple, 10, 12, 14 years, it has been a more flat, I don't want to use the word flat, going up less than the previous decade. Last November was the warmest November on record. Last year was in the top 6 or 7, I think, on record of warm years. Of the last, I forgot the exact numbers, but the top 10 warmest years have all occurred in the last 20 years or 15 years. And there's no doubt that it's warmer now than it was a couple decades ago, and every year is getting warmer pretty much. But there is a bit of a flattening out of the curve. But what you have to understand is of this heat that lands on the surface, some of it goes into the atmosphere and heads back towards outer space, but some of it stays in the Earth. And the atmosphere interacts with the ocean. So a lot of this heat actually ends up in the ocean. Whether the ocean is sucking in more heat than average or releasing more heat than average is one of the things the ocean does. It's a decadal long thing. The Southern Oscillation, El Nino, La Nina, that kind of thing. Right now, the oceans in the Pacific tends to be bringing in more heat than average, or it's average or more heat going into the ocean over the last few years. Also, when you melt ice, you don't get that heat in the atmosphere. We're using heat to melt ice. And there's a lot of ice melting. So between the ocean sucking in a lot of heat and, the ocean takes in over 90% of the heat that the sun produces. Most of it goes in the ocean. So when we measure the surface temperature, the thing we usually use, the curve you usually look at is the surface temperature, which is all the weather stations plus the sea surface. That is like going to the Mall of America and saying, I want to estimate how good business is at the Mall of America. So what I'm going to do is I'm going to set up at one doorway and just count how many people go in and out. Mm-hmm. That would work. You would notice a lot more people going in and out at Christmas time. When there was a big sale, Columbus Day, there'd be more and more people going in and out on those days, and you would be able to estimate the overall business in that mall. But if they change the configuration inside the mall, and that's no longer a good place to park,
right, yeah,
you're going to get a spurious change, plus it's a small sample. Well, by looking at the surface temperatures only, we're doing that. We're looking at a small part of the bigger picture. Well, most of the heat goes into the oceans, over 90%. And we haven't been measuring the deep oceans. And it turns out that when you do measure the deep oceans, they seem to be warming kind of dramatically.
Have the deep oceans been being measured for very long?
No, we didn't even know where they were like 100 years ago.
Yeah, right.
People didn't know that there was a deep ocean. They just knew that there was the land and then there was the ocean, and they didn't know about the continental margins and all that stuff. And the technology to go deep is even limited now. I mean, you can't go out and measure it. It's very limited what we can even do now. And the deep exploration didn't start till the 60s. You know, Jacques Cousteau and the bathysphere and all that. So even coring at the bottom of the ocean was limited to the continental shelves and shallow regions until the late 60s. And there are not measuring devices down there for the most part. So we have very little data on deep ocean temperatures.
So we just have a few minutes left in this half. Okay. So can you maybe tell viewers and listeners some ideas of websites they could visit if they wanted to find out more about climate change?
The one website that has been established and has been there for a long time, in which the people who write it specifically take questions that people have and convert them into web pages that address them. And in some cases, there's a beginner, intermediate, and advanced tab you can choose, which one you get more math.
Where
basically.
Do they get these questions from?
There's just out there in the literature, people in the news, people saying, oh, global warming is not real because of this, or global warming is not real because of that sort of thing. It's called skepticalscience.com. And I'm not affiliated with it, but I know the people who do it. And they do a very good job. There's climate scientists, and they do a very good job of explaining things very thoroughly. And it's even though I write about the stuff in my blog, I tend to send people there instead because it's better.
Okay.
And then another project that's just John Irving and some other people and I have been developing a little bit. There's a Facebook page called Global Warming Fact of the Day, which is a fun Facebook page with people where we all put our links to things on it. And now there's a website called Global Warming Fact of the Day, which has basically everything about global warming that's come out in recent days. It's a feed. Fire hose feed, and we're working
up to the minute.
Yeah. Literally. And we are now organizing a resource page which will have that feed called out. So 1 in 100 items that we think are long value, posts. You want to know about a certain aspect of climate change. Here's the 2 or 3 good pieces of writing on it, and so on. And plus, there's a few other blogs out there that are great. The Guardian has a good blog. John Abraham, who's here from the University of St. Thomas, co-authors a blog at the Guardian on climate change, and there's a lot out there on the internet. But if you start with Global Warming Fact of the Day, you can see where the good writing is. And any questions that come up, you can go to skepticalscience.com, and I'll have some stuff. I always have stuff on my website too.
So if I type in Global Warming Fact of the Day in Facebook, will I be able to find it?
Yes,
there?
You will. And on the internet, it's a new site, so it hasn't gotten any Google juice yet, but it's GWFOD or whatever it is, I think, .com.
Yeah, I think we're going to put the links up on the screen for people who are watching it. And then your own blog as well? You want to mention how people can get there? Yeah,
it's Greg Laden's blog on Science Blogs. I didn't want to name it that originally. That's what they named it, just so you know. I was going to call it something with evolution in it. My original blog name was Evolution, Not Just a Theory Anymore. But there are already 5 blogs with the word evolution in them in Science Blogs.
Okay, yeah.
But I write, lately these days, in fact, when I write about science, I write a bit about atheism and politics now and then, but when I write about science, it's these days mostly about climate change.
Okay.
Not entirely, but mostly.
That reminds me that when people talk about climate change, they sometimes attribute storms to climate change. And maybe we can get to this more in the second half, but maybe you can touch on that for just a couple minutes real quick. Like, does global climate change affect storminess?
The original. There's a lot we can talk about that. We'll probably talk about more in the next section, but until recently, I think people who are talking about climate change were coached to say you can't attribute climate, you can't take any given weather event and attribute it to climate change. Because climate is the 30-year-long trend and
picture.
Weather is this weekend. But we've realized that it's actually the opposite is true. You can't take a weather event. If climate has fundamentally changed, it's very hard to take a weather event and remove the climate from it. I mean, it's cold out now. It's exceptionally cold right now in Minnesota tonight. But it's also winter. Mm-hmm. So we're not surprised that it's cold. Yeah. The fact that it's winter, that's climate. The fact that it's cold makes sense because it's winter. The fact that it's extra cold is an annoyance. And by the way, this extra cold we're having is the result of climate change, probably. Oh, okay. We're having some weather patterns that are probably induced by climate change. And the explanation is kind of complex. And the current storms, as we're recording this now, the East Coast is being hit with major storms that could turn into big blizzards in New York, in that area. And there may be a climate change effect there. But I think the thing is now, climate is changing enough because of the changes in the chemistry of the atmosphere and the physics of the atmosphere that it's impossible to really remove the effects of climate change from any given weather event.
Okay. I just thought we had a couple extra minutes, so maybe we could touch on that, but we can talk more about that in the second half. And then, of course, if people, especially if you're watching this, if you want more information, you can just go to the blogs and the websites and the Facebook page that Greg just talked about that are going to be displaying on screen. So I'd like to thank you for watching the show. And if you would like to contact us at any time, if you have any questions or if there's anything that you would like to see presented, please let us know. We'll be happy to send you a copy of our newsletter if you contact us, because if you're interested in us, we're interested in you. Be sure to watch the second half of this program on climate change with Greg, Laden, and I, and we'll talk to you later. Thank you.